Welcome! In this session, we'll be solving problem number 1063, number of valid subarrays. This problem challenges us to count all subarrays of a given array that are sorted in non-decreasing order. We'll explore how to approach this task efficiently. Let's get started. In this problem, we are tasked with finding the number of valid subarrays in a given integer array nums. A subarray is defined as a contiguous portion of the array, and it is considered valid if its elements are sorted in non-decreasing order. Non-decreasing means that each element in the subarray is less than or equal to the element that comes after it. The goal is to calculate the total number of such valid subarrays in the input array. The input will be an integer array nums of length n, and the output will be a single integer representing the count of valid subarrays. To illustrate this, let's consider an example where nums is equal to 1, 4, 2, 5, 3. The output in this case is 11, and this number comes from counting all valid subarrays. For instance, 1 is valid because it contains a single element, and single element subarrays are always valid. 1, 4 is also valid since 1 is less than 4, maintaining the non-decreasing order. Similarly, 4, 2, 2, 5, 5, and 3 are all valid subarrays. When we list out all valid subarrays, we find that there are 11 in total. Now, let's examine another example where nums is 3, 2, 1. Here, the output is 3. This is because each element forms its own valid subarray, as single element subarrays are always valid. However, no larger subarrays can be valid, since the array is strictly decreasing, meaning the non-decreasing condition is violated. Thus, the valid subarrays are 3, 2, and 1, for a total of 3. Let's look at one more example, where nums is 2, 2, 2. In this case, the output is 6. Here, not only are the single element subarrays, 2, valid, but so are the larger subarrays that include repeated elements. For instance, 2, 2, and 2, 2, 2 are valid because all elements are equal, which satisfies the non-decreasing condition. By counting all valid subarrays, we get a total of 6. To summarize, the problem has some important constraints and edge cases to consider. The constraints specify that the array length can go up to 10,000, and the elements can range from 0 to 100,000. For edge cases, if the array has only one element, the result is always 1 because a single element array is inherently valid. If the array is strictly decreasing, each element forms its own valid subarray, resulting in n valid subarrays. On the other hand, if the array is strictly increasing, every prefix of the array forms a valid subarray, leading to a total of n asterisk, n plus 1/2 valid subarrays. Finally, for arrays with repeated elements, we count all combinations of consecutive repeated elements as valid subarrays, provided they maintain the non-decreasing order. To tackle the problem of counting all valid subarrays that are sorted in non-decreasing order, several approaches can be considered. One of the most intuitive methods is the brute force approach. In this approach, we systematically generate all possible subarrays from the given array. For each subarray, we verify if the elements are sorted in a non-decreasing order. This involves looping through every starting index of the subarray, then looping again for every possible ending index. For each combination, we extract the subarray and check its order by iterating through its elements. If the subarray meets the condition, we count it as valid. While this approach is straightforward and easy to implement, its computational cost is a concern. Generating all subarrays takes n squared time, and checking each subarray adds another n, resulting in an overall time complexity of n cubed. Additionally, it has a space complexity of 1, since no additional data structures are used. However, this inefficiency makes it unsuitable for large inputs, particularly when the array size can go up to 10,000 elements. The brute force approach, while simple, becomes infeasible for larger arrays due to its cubic time complexity. This leads us to consider optimized solutions, such as using a monotonic stack. A monotonic stack allows us to count valid subarrays in linear time by leveraging a key observation about the problem. The idea is that if an element nums, j, is the rightmost element of a valid subarray, then all elements to its left that are greater than or equal to nums, j, can extend this subarray. To implement this, we initialize an empty monotonic stack that maintains elements in non-decreasing order. As we iterate through the array, we check if the current element is smaller than the top of the stack. If it is, we pop elements from the stack until the condition is satisfied. Then, we push the current element onto the stack. At each step, the size of the stack represents the number of valid subarrays ending at the current index, and this count is added to the total result. This approach is highly efficient, with a time complexity of O(n), since each element is pushed and popped from the stack at most once. The space complexity is O(n) due to the stack, which is used to dynamically track elements. This optimized stack-based approach is highly efficient because it eliminates the need for nested iterations by dynamically tracking valid subarrays as we traverse the array. By maintaining a monotonic stack, we ensure that we only compute counts for subarrays ending at each index, drastically reducing the computational overhead. The monotonicity property of the stack is key to this efficiency. Comparing the two approaches, the brute force method, while intuitive, is impractical for large inputs due to its O(n)³ complexity. On the other hand, the optimized solution leverages the monotonic stack to achieve linear time complexity, making it a clear winner. The breakthrough insight, or the aha moment, comes from realizing that we don't need to generate all subarrays explicitly. Instead, we can count valid subarrays ending at each element dynamically. In terms of trade-offs, the brute force method is simpler to understand and implement but fails to scale with larger arrays. The stack-based approach, while slightly more complex, is significantly faster and better suited for the problem's constraints. Given these factors, the monotonic stack approach is the ideal choice, balancing efficiency and maintainability effectively. In this problem, we aim to determine the number of valid subarrays in a given array, or a subarray is valid if it is sorted in non-decreasing order. For example, in the array 1, 4, 2, we have 5 valid subarrays, 1, 4, 2, 1, 4, and 2. To solve this efficiently, we use an optimized approach based on a stack. The idea is to use the stack to track indices of elements that can serve as starting points for valid subarrays, and by doing so, we can calculate the total number of valid subarrays in linear time. First, we initialize an empty stack and a counter variable count to 0. The stack will help us maintain indices in a way that ensures we only consider non-decreasing subarrays. Then, we iterate over the array, processing each element one by one. As we iterate over the array, for each element nums I, we check whether the stack contains indices of elements that are greater than nums I. If so, we pop indices from the stack, as those elements cannot form valid subarrays ending at I. Once the stack is updated, we push the current index I onto the stack. At this point, the size of the stack represents the number of valid subarrays that end at index I, because each index in the stack indicates a valid starting point. We add this stack size to our count variable, incrementing the total number of valid subarrays. Finally, when the loop completes, we return the value of count. The stack's role here is crucial. It ensures that we efficiently track indices of potential starting points while maintaining the non-decreasing order required for valid subarrays. By adding the stack size at each step, we capture all valid subarrays ending at the current position without redundant computations. To better understand this, let's walk through an example with nums equals 3, 2, 1. We start with an empty stack and count set to 0. For the first element, nums 0 equals 3, the stack is empty, so we simply push index 0 onto the stack. Now, the stack contains 0, and count becomes 1, representing the subarray 3. Next, for nums 1 equals 2, we notice that the top of the stack corresponds to an element greater than 2. So, we pop the index 0 from the stack and then push index 1. The stack now contains 1, and count is updated to 2, reflecting the subarray 2. Similarly, for nums 2 equals 1, we again pop the stack because 2 is greater than 1. We push index 2 onto the stack, leaving 2 in the stack, and increment count to 3, which corresponds to the subarray 1. This example illustrates how the stack helps us efficiently compute valid subarrays by maintaining the necessary order and avoiding redundant checks. Analyzing the complexity, the time complexity of this solution is O(n), because each element in the array is pushed and popped from the stack at most once. The space complexity is also O(n), as the stack stores indices of potential starting points. Let's consider a few edge cases. If the input array is empty, we simply return 0, as there are no subarrays. For an array with one element, the result is 1, since there's only one subarray. For a strictly increasing array, each element contributes to all subarrays ending at its position, resulting in a sum of all consecutive integers. In contrast, for a strictly decreasing array, each element forms its own subarray, as no two elements can form a valid subarray. Finally, the Python implementation of this approach is shown here. It uses a simple loop to iterate over the array, with stack operations to maintain the non-decreasing order and a counter to track the total number of valid subarrays. This implementation is both efficient and concise, making it well suited for solving this problem in practice. This Python implementation solves LeetCode problem number 1063, number of valid subarrays, using an optimized approach with a stack. The goal is to count all valid subarrays where each subarray is sorted in non-decreasing order. The solution uses a single pass through the input array nums, maintaining a stack to keep track of elements in the current valid subarray. Here's how the algorithm works. 1. Initialization. The stack is used to store elements of the current valid subarray, and count keeps track of the total number of valid subarrays. 2. Iterate through nums, for each element number in the array. Remove elements from the stack.pop, that are greater than number. This ensures that the stack only contains elements satisfying the non-decreasing order property. Append the current element number to the stack. Add len, stack, to count. This step calculates the number of valid subarrays that end with number. The size of the stack represents the count of valid subarrays ending at the current index. 3. Return the result. After processing all elements in nums, the variable count holds the total number of valid subarrays. This approach is efficient because each element is pushed and popped from the stack at most once, resulting in an overall time complexity of O(n), where n is the length of the input array. The space complexity is O(n) due to the stack. The stack-based solution avoids generating all subarrays explicitly, making it suitable for large input sizes. It handles edge cases like empty arrays and arrays with identical elements correctly. This is the Java implementation for the LeetCode problem number of valid subarrays. The logic mirrors the given Python solution, using a stack to track valid subarrays. Key differences include explicit type declarations, using Java's stack class, and Java-style loops. The stack helps efficiently calculate the count of valid subarrays ending at each element, ensuring an optimal solution. Here, we are given the input array nums equals 1, 4, 2, 5, 3. We start by initializing an empty stack and setting our count to 0. Now, as we process each element in the array, we first encounter 1. Since the stack is empty, we append 1 directly to the stack. This gives us a stack of 1. The size of the stack, which is 1, is then added to our count, resulting in a total count of 1. Next, we process 4. The top of the stack, which is 1, is less than 4, so we append 4 to the stack. The stack now becomes 1, 4. We then add the size of the stack, which is 2, to our count. This updates the count to 3. Now, we move on to processing 2. Here, the top of the stack, 4, is greater than 2, so we pop 4 from the stack. This leaves us with 1. After that, we append 2 to the stack, making it 1, 2. We then add the size of the stack, which is 2, to our count, bringing the total to 5. Next, we process 5. The top of the stack, 2, is less than 5, so we append 5 to the stack. The stack becomes 1, 2, 5. The size of the stack, which is 3, is added to our count, resulting in a count of 8. Finally, we process 3. The top of the stack, 5, is greater than 3, so we pop 5, leaving us with 1, 2. We then append 3 to the stack, resulting in 1, 2, 3. Adding the size of the stack, which is 3, to our count gives us the final count of 11 for this example. In the second example, the input array is nums equals 3, 2, 1. We start by initializing an empty stack and setting the count to 0. First, we process 3. Since the stack is empty, we append 3 to it, resulting in a stack of 3. The size of the stack, 1, is added to our count, making the count 1. Next, we process 2. The top of the stack, 3, is greater than 2, so we pop 3 from the stack, leaving it empty. We then append 2 to the stack, making it 2. The size of the stack, 1, is added to the count, bringing it to 2. Continuing with the same example, we now process 1. The top of the stack, 2, is greater than 1, so we pop 2, leaving the stack empty again. After that, we append 1 to the stack, resulting in 1. The size of the stack, which is 1, is added to the count, giving us a total count of 3. For the final output of this example, we return 3. Moving to the next example, we now consider nums equals 1, 2, 3. Here, we initialize the stack as empty and set the count to 0. First, we process 1. Since the stack is empty, we append 1 to it. This results in a stack of 1. The size of the stack, 1, is added to the count, making the total count 1. Next, in the third example, we process 2. The top of the stack, 1, is less than 2, so we append 2 to the stack. The stack becomes 1, 2. The size of the stack, which is 2, is added to the count, bringing the total to 3. Finally, we process 3. The top of the stack, 2, is less than 3, so we append 3 to the stack. The stack now becomes 1, 2, 3. The size of the stack, which is 3, is added to the count, giving us a final count of 6 for this example. Thus, the output for this input is 6. For the time complexity analysis, we start by examining the outer loop. This loop iterates through each element in the input array nums, so it contributes O(n) to the overall complexity. Within this loop, there is a while condition that checks whether the top of the stack is greater than the current number. When this condition is true, elements are removed from the stack. However, each element in the array is pushed onto the stack only once and popped at most once. This means the total number of stack operations, including both pushes and pops, is bounded by n. Therefore, the while loop also contributes O(n) in total. Additionally, the stack.append number operation is executed once per iteration of the outer loop, which adds O(1) per iteration. Over n iterations, this gives another O(n). Lastly, the count plus equals len stack operation occurs in constant time per iteration because computing the length of the stack is an O(1) operation. Across all iterations, this adds a final O(n) to the total complexity. Now, when we add up the contributions from all the operations, the total time complexity is O(n) from the outer loop, O(n) from stack operations, O(n) from stack appends, and O(n) from the count updates. This simplifies to an overall time complexity of O(n). This approach is optimal because each element is processed at most twice, once when it is pushed onto the stack and once when it is popped. Moving on to space complexity, the main contributor here is the stack. In the worst-case scenario, where the input array is sorted in non-decreasing order, all elements will be pushed onto the stack, leading to a maximum space requirement of O(n). Apart from the stack, we use only scalar variables like count and number, which occupy constant space, or O(1). These scalar variables do not depend on the size of the input array. Given this breakdown, the overall space complexity is dominated by the stack, resulting in O(n) in the worst case. Let's consider the best, average, and worst-case scenarios. In the best case, where the array is strictly decreasing, each element is pushed and then immediately popped from the stack. Although the stack size remains small, the time complexity is still O(n) due to the linear traversal. For random inputs, the stack size fluctuates depending on the relative values of the elements, but the amortized time complexity remains O(n). In the worst case, when the array is sorted in non-decreasing order, all elements are pushed onto the stack, and no popping occurs, leading to a stack size of n. However, even in this case, the time complexity remains O(n). Comparing this to a naive approach, where we generate all subarrays and validate each one, the naive method would involve O(n squared, or worse due to the sheer number of subarrays and the comparisons required. By using a stack, this solution avoids redundant operations and computes the result in linear time, making it far more efficient for large inputs. When solving this problem, there are several common mistakes to watch out for. First, it's essential to account for single-element subarrays. Each of these is inherently non-decreasing, so failing to include them can result in an undercount, especially in edge cases like arrays where all elements are distinct or identical. Another common error is relying on nested loops to evaluate each subarray individually, which leads to an O(n)² time complexity. This approach is not suitable for large inputs, as it can result in time limit exceeded errors, especially when the array length exceeds 10 cubed. Additionally, some might misinterpret the term non-decreasing as strictly increasing, which would exclude valid subarrays where consecutive elements are equal. This misunderstanding directly violates the problem's requirements and leads to incorrect results. Lastly, when using optimized approaches such as a stack, it's crucial to manage the count correctly. Forgetting to reset or update the count when encountering a decreasing element can cause logical errors, resulting in either overcounting or missing valid subarrays altogether. Another frequent issue is failing to handle edge cases. Examples include empty arrays, arrays where all elements are identical, or arrays sorted in strictly decreasing order. Neglecting these scenarios can cause runtime errors or inaccurate results. From an interview perspective, this problem tests your ability to recognize key patterns, such as the monotonic properties of sequences. It's important to understand that you can efficiently count valid subarrays without explicitly generating them. The optimal solution typically involves an O(n) approach using either a stack or a sliding window. This avoids unnecessary computations while maintaining clear and efficient logic. Be prepared to explain the trade-offs between naive and optimized methods. For example, while the brute force approach is straightforward, it's impractical for large inputs, whereas optimized methods like stacks leverage the properties of non-decreasing sequences for better performance. Additionally, interviewers often test your ability to handle edge cases, so focus on how your solution addresses tricky scenarios, such as arrays with repeated elements or single-element arrays. Understanding related problems can help reinforce the concepts needed to solve this one effectively. For example, problems like LeetCode 1124, longest well-performing interval, and LeetCode 907, sum of subarray minimums, involve similar techniques for managing subarrays. LeetCode 239, sliding window maximum, and LeetCode 581, shortest unsorted continuous subarray, also share overlapping ideas, such as using stacks or sliding windows. When considering alternative approaches, the brute force method is a straightforward option. This involves iterating through all possible subarrays and checking if each one is non-decreasing. While this is simple to implement, it comes with a significant trade-off: its O(n)² time complexity makes it unsuitable for large arrays. On the other hand, the optimized stack-based approach offers an efficient O(n) solution. By maintaining indices of elements in a stack, you ensure the order remains non-decreasing while counting valid subarrays dynamically. However, this method can be slightly more challenging to implement and debug compared to brute force. Another efficient method to solve this problem is the sliding window technique, which also runs in O(n) time. With this approach, you use two pointers to define the boundaries of a non-decreasing window, dynamically updating the count of valid subarrays as you move through the array. This method has the advantage of being conceptually simpler than the stack-based approach, but it does require careful implementation to avoid common pitfalls like off-by-one errors. Both the stack and sliding window techniques are powerful tools for this type of problem, and understanding their trade-offs will not only help you solve this problem optimally but also prepare you for tackling similar challenges in the future. Great job! To wrap up, we reviewed the key concepts and takeaways from solving number of valid subarrays. Remember to practice similar problems to strengthen your understanding. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!